So in today's lecture, we are going to solve the differential equation and look at the exponential of a matrix. So differential equations. And EAT, an exponential of a matrix. How do we compute the exponential of a matrix? For differential equations, just like the difference equations, for differential equations, u of t equals EAT u naught. Depends on exponential of a. So let's see how do we calculate this one. So let's look at an example first. So du over dt equals au, which is equal to minus 2 1 1 minus 2. This is a symmetric matrix, so we should have a full set of eigenvectors. U, so you should look at the matrix and then you should know what the answer should be so that you can check whether your calculations are correct or not. So let's find the eigenvalues of a minus lambda I. The determinant is minus 2 minus lambda 1 1 minus 2 minus lambda, which implies minus 2 minus lambda whole square minus 1 whole square. So again, using the same trick, this is a square, this is b square. So we have a minus b, a square minus b square equals a minus b into a plus b. So you shouldn't always expand the equation as is. You just should look at this at the simplification that you can do before expanding the equation. So this one is, so minus 2 minus lambda minus 1, a minus b, a plus b. So this one is lambda 2, this is lambda, or maybe this is lambda 1, this is lambda 1, this is lambda 2. So this implies lambda 1 equals minus 3, and this implies lambda 2 equals minus 1. So maybe I shift these from my convention to the largest value goes there. So this is lambda 2 and this is lambda 1. So lambda 2 is minus 3 and lambda 1 is minus 1. And what are the eigenvectors? So this implies a minus lambda 2 I into x2 equals 0, or this means or a minus lambda 2I minus 3. So minus 3 plus 3, 3 minus 2 is 1. This is 1. This is 1. Minus 2 plus 3, this is 1. And I can always do minus rho 1 plus rho 2. This will give me 1 1 0 0. This is my pivot. So this implies x2 is going to be equal to minus 1 1. So this one comes over here, becomes a negative 1. Okay, and what about this one? This implies a minus lambda 1 I into x1 equals 0, or minus 2 plus 1 minus 1 1 1 minus 2 plus 1 minus 1. Again, I do row 1 plus row 2. If I do row 1 plus row 2, I have minus 1 1 0 0. And then I do row 1 divided by minus 1. If I do that, I put a minus here, I put a plus here. This is a pivot, just like this is a pivot, and this implies x1 equals 1 1. Okay, this minus 1 goes here, becomes a plus. So negative here, negative here. Okay. And what is s? Or maybe I'll calculate s later on. Or u of t is we know from the first example that we did when we started this chapter was the complete solution is C1 E lambda 1 t x1 plus C2 E lambda 2 t into x2. This is from first example of chapter 5. So look at the first video lecture and you'll see this one, or vector u equals c1. We have to calculate c1, and before we do that, or maybe how do we calculate c1, or maybe u0. Do I have u0? I don't have u0. So or u0 is c1 x1 plus c2 x2, which is equal to s into x2. S is 1 1, and then this one is minus 1 1 into c1 c2. This is s, this is c. This is equal to s times c. And so we can't find u1. We can't find, so we have to have u1 of u naught, or recall, or since u of t equals EAT u naught. So this is from here, u of t is equal to EAT u naught. So this is equal to S E lambda t S inverse u naught, or this is equal to x1 xn E lambda 1 t E lambda n t, and you have to bear with me how did I equate these two. And then S inverse u naught is simply C1 C naught, or u naught equals SC. This implies C equals S inverse u naught. So S inverse u naught is equal to some C, or for our case, or in our case, u of t equals S, which is 1 1 minus 1 1 E minus t E minus 3t, right? And you can again check here. The eigenvalues are minus 3 and minus 1, which is minus 4. So sum here is minus 4. The determinant of this one is 4 minus 1, which is 3. And the product here is minus 3 minus 1, which is 3. So these eigenvalues are all right. So, and this one is S inverse U naught. This one is S inverse U naught, which is C1, C2, which is equal to C1, and C2. So this one we can write this as E minus t, or this is 2 by 2, this is 2 by 1. So this whole thing is C1 E minus t, or maybe I multiply this one first. Maybe it's easier if I multiply this one first. So if I do this one first, this one is E minus t here, and E minus t plus 0, and this is minus E minus 3t. So E minus t on the first one, and E minus 3t here. And when this is multiplied by C1, C2, so we have C1 E minus t minus C2 E minus 3t, and C1 E minus T plus C2 E minus 3T. This is my U. Right? This is U of T. So we have actually, when you multiply this one, so this column is weighted by this one. So we have E minus T here. And then when this is weighted, so we have minus E minus 3T and plus E minus 3T here. So this one multiplied by C1 and C2. So C1 is here, C1 E minus T minus C2 E minus 3T, C1 E minus T plus C2 E minus 3T. So unless you know the initial condition, you can't find C1 and C2. So S E lambda T S inverse U naught solves the differential equation, just as S lambda K S inverse U naught solve the difference equation. Or this implies U of T is S E lambda T S inverse U naught with gamma or lambda equals to -1 -3 and E lambda T equals to E minus T and E minus 3T. So we still need to figure out how did we get E lambda T as E minus T, E minus 3T. Okay, so what is the matrix exponential? So what is the matrix? How do you compute the matrix exponential? EAT equals, so recall, maybe we do it before we do that. Recall, what is e raised to the power x? E raised to the power x is the series x raised to the power k over k factorial. K goes from 0 to infinity, which is equal to x0, which is 1, plus x square over 2 factorial plus x3 over 3 factorial plus so on and so forth. Okay. So this implies EAT should be equal to, if x is equal to AT, so instead of 1, I have an identity matrix, plus x is AT plus A square T square over 2 factorial plus A cube T cube over 3 factorial plus so on and so forth. This series always converges. This series always converges. Also e raised to power as into e raised to power at is equal to e into a into s plus t. EAT into e minus at is identity. So this is the inverse. It's the inverse. And d by dt of EAT is simply a times EAT, or it's EAT times a. Right? It's equal to EAT times they both commute. Both commute with each other. Now, EAT equals I plus S lambda inverse T plus S lambda square S inverse T square over 2 factorial plus so on and so forth. This I is equal to S into S inverse. This I is equal to, so I can take S out on this side, I can take S inverse out on this side, S on this side, S inverse on this side. So I'll get S I plus lambda t plus lambda square t square over 2 factorial plus lambda cube t cube over 3 factorial plus S inverse. And what is this thing? This thing says simply E lambda t. This is by definition E lambda t. So this implies E a t equals S E lambda t into S inverse. And what happened to our solution? If I assume and there is one more, and here e raised to power 0 is identity. E raised to power 0 is identity. So if t is equal to 0, this is identity. What happened to our case there? So I need to find, or maybe I just find EAT. EAT then. So from our previous example, from our previous example, EAT is equal to S E lambda S inverse, which is equal to S was 1 1. Let me see. S was 1 1 minus 1 1. S was 1 1 minus 1 1. This was E minus t. This was E minus 3t. And this was the inverse of S. So let me write. So this is S. This is E lambda t. And this is S inverse. Determinant of S was, so determinant of S where determinant of S is 1 plus 1, which is 2. So there is a half somewhere here. This is this one. And when you exchange it, this will be 1, 1, this will be 1, this will be minus 1. Okay. And when I expand this one, this becomes E1. So when I multiply this one, this will be E minus t minus E minus 3t, E minus t with a half here, and E minus 3t. This one multiplied by 1, 1 minus 1, 1. And this will become, so this will be a 2 by 2 case. So 1 is multiplied by this one, and minus 1 is actually multiplied by this one. So I have E minus t plus, so E minus t plus E minus 3t divided by 2. And then I have E minus t minus E minus t minus E minus 3t divided by 2. Then this one goes to this one. So again, same here. So this is E minus t minus E minus 3t as is divided by 2. And this is E minus t plus E minus 3t divided by 2. So this is E raised to power a t. So if A can be diagonalized, this implies A is S lambda S inverse, then du over dt, which is equal to AU, as a solution U of t equals EAT U naught, which is equal to S E lambda t S inverse U naught, which is equal to S E lambda t into C, where C is S inverse U naught, or this is equal to If you multiply out, this is C1 E lambda 1t x1 plus C2 E lambda 2t, or maybe if you want me to, I can write it explicitly. This is equal to x1 xn E lambda 1t E lambda nt, and then I have C1 Cn, or this is equal to C1 E lambda 1t x1 plus C2 E lambda 2t x2 plus so on plus Cn E lambda nt xn. So it's a combination of E lambda t. So this one, or this implies U of t is a combination of E lambda I t, E lambda I t's. So obviously stability will depend on E lambda I t, or most likely the real part of lambda I. So if we see that in a little while. So if a complete set of eigenvectors, if a complete set of eigenvectors does not exist, then solutions are of t times E lambda t form. T times E lambda t form, that is Jordan form. That is the Jordan form. However, U of t equals EAT U naught is still correct. It's E lambda t. Instead of this lambda, we have the Jordan form EJT. We have the Jordan form. I can give it to you, write it for you, EJT. We have EJT. We have EJT. That is EJT. Okay. EAT is non-singular, is always non-singular, because if lambda is an eigenvalue, of A, then E lambda t is the corresponding eigenvalue, of EAT. However, E lambda t can never be zero. So EAT is always non-singular. Or if you want to find the determinant, EAT, the determinant is the determinant of S, the determinant of E lambda t, and the determinant of S inverse. This one cancels out, then cancel out, and this is simply E lambda t, which is E lambda 1t into E lambda 2t into E lambda nt, which is equal to E t lambda 1 plus lambda 2 plus lambda n t, which is equal to E times of A into T, right? Also inverse of EAT is equal to E minus AT, because EAT into E minus AT is equal to E0, which is equal to I. What about the stability? So stability follows closely the stability results of the difference equation solution, and which are, and I'll just write them. So eigenvalues, so stability. So eigenvalues decide how u of t behaves as t tends to infinity. So as long as a can be diagonalized, as long as a can be diagonalized, there will be n pure exponential solutions. There will be n pure exponential solutions to the differential equations, and any solution u of t is some combination. And what is that combination? U of t equals S E lambda t S inverse u naught, which is equal to C1 E lambda 1 t x1 plus C2 E lambda 2 t x2 plus Cn E lambda n t xn. So this implies stability is governed by E lambda I t. So stable if EAT tends to 0 as t tends to infinity, implies all real lambda I is less than 0. So we are actually in the left half plane, if you can look at that. So versus lambda I less than 1. So this is for the difference equation case. And neutrally stable if all real lambda i's are less than equal to 0 and real lambda 1 is equal to 0, versus lambda 1 equals to 1 and lambda I less than 1 is less than 0. And unstable implies EAT is unbounded if at least one real lambda I is greater than 0 versus lambda I greater than 1. Right? So instead of the absolute value, we are interested in the real part, whether the real part is negative or real part is 0 or real part is greater than 0. So if you recall from lecture 1, real part is the one that controls the decay. So if alpha I, so if lambda I is alpha plus j beta, so this is the one we are interested in, and this controls rate of growth or decay. This is from first lecture of chapter 5. Okay, so let's look at another example. What happens if the matrix is symmetric? Maybe we have some simplicity, we have simplifications. For example, du of dt is a, b, c, d, and this is some u. So c, d, and this is some u. So what are the stability tests? So stability tests are trace of A, this is A, is equal to A plus D, should be negative because then the eigenvalues are negative. Excuse me. And the determinant of A, which is AD minus BC, this must be positive. And let's see why. Because A minus lambda I determinant is A minus lambda into D minus lambda minus BC, which is equal to lambda square minus lambda into A plus D plus AD plus AD minus BC. So this is equal to lambda square minus trace A times lambda plus determinant of A, or lambda 1 comma 2 equals trace of A plus minus under root trace of A, this is B square, so trace of A square minus 4AC minus 4 times determinant of A divided by 2. Okay. So if I plot this equation, this is trace of A, or maybe just write trace. This is trace of A. This is determinant of A, and I have this exponential. And what is this thing? This is where trace of A square, this is where trace of A square is equal to 4A, determinant of 4A, and this is the point where lambda 1 equals lambda 2. So when this part is equal to 0, then we have repeated. So we have repeated eigenvalues. Okay, good. And if so, on this point, trace is equal to the determinant. Over here, trace is greater than. So if the trace is equal to the determinant, here trace, the determinant is greater. So here we'll have this one. So here the discriminant in this portion, the discriminant is negative. So trace of A whole square is less than 4 times determinant of A in this portion. In this portion, trace of A square is less. So we have complex, implies complex eigenvalues. If we have complex eigenvalues, so if this is less than, so we have complex eigenvalues. So here we have a real part of lambda lambda, so complex eigenvalues lambda say. So real of lambda is less than 0, and here real part of lambda is greater than 0, both, and this one is stable and this one is unstable. And here in this portion, here the trace is greater than this one, trace is greater than the determinant. So here trace is, so in this one, trace of a square is greater than 4 times the determinant. So this implies you have real solutions. So when you have real, but the trace is positive, so this means unstable. So here trace, this is unstable. Why? Because trace is positive. So because this is what we said, trace is negative, so that the eigenvalues, the real part is negative. So this is unstable, and both lambda greater than 0. Here obviously we have stability because trace is negative here. So here we have stability, trace is negative, and both lambda less than, less than 0. So they are, both lambda are real, and that's in. So both lambda here is real, and so below this curve it's real eigenvalues, on this it's repeated eigenvalues, and inside this is complex eigenvalues. Is this right? Yes. And this is actually, by the way, this is called the discriminant, if I'm correct. This is the discriminant. So based on the discriminant, we can have, we can solve this quadratic and see whether we have complex roots or real roots. So every symmetric matrix has real eigenvalues, and this is true whether the elements are real or complex, has real eigenvalues, because B equals C. So in this case, this is equal to this one. So we have, if I expand this one, so A minus lambda I, so trace of A square minus 4 times the determinant equals, so trace of A is A plus B whole square minus 4 times the determinant is 4 into AD minus B into C, but since B is equal to C, I will replace this by B square. Okay. So this becomes A square plus D square plus 2AD minus 4AD plus 4BC. So this is equal to A minus B whole square plus, or B square, sorry, plus 4B square plus 4B square plus 4B square. So this term is positive, this term is positive. So this means, this implies trace of A whole square minus 4 times A under root is a positive number, is a positive real number, is a real number. It's not a positive, it can be both positive, negative, is a real number, and since trace of A is also real, this implies lambda 1, 2 are real. So for a symmetric matrix, the eigenvalues are always real. Okay, so let's look at an example. du by dt equals, so this is a rotation matrix where u0 is 1 and 0. So if you recall, this is the K matrix, this is the rotation matrix, rotation by 90 degrees, rotation by 90 degrees, and so k minus lambda I determinant is minus lambda square plus 1 equals 0. This implies lambda square is equal to minus 1, which is equal to iota square. This implies lambda 1 is equal to plus I, and lambda 2 is equal to minus I. And recall x1, recall from second lecture, x1 equals 1 iota, 1 minus iota, and x2 from lecture 2, and x2 equals 1 plus iota. And I can quickly calculate what is S inverse, where S is 1 minus iota, 1 plus iota. Determinant of S is iota plus, so it's 2 iota, and S inverse is equal to 1 over 2 iota into iota 1 minus 1 plus iota, which is equal to half plus iota over 2, half minus iota over 2, right? And what is C inverse? And S inverse, and S inverse C is where C is 0 and 1, or 1 0. 1 0, since this is 1 0. S inverse U naught, and C equals S inverse U naught, which is equal to, since this is U naught is 1 0, we only have the first one, half. This is C1, this is C2. So this implies U of t is half E iota t into x1, 1 minus I, plus half E minus iota t into 1 plus iota. And this is x2, this is E lambda 2t, this is C2, this is x1, this is E lambda 1t, and this is C1. Okay. And if I solve this one, this will become, so recall E iota t is cosine of t plus iota sine of t. This is the Euler's identity. So U of t, so this implies U of t is simply half E iota t plus half E minus iota t, which is simply equal to, so these are conjugates of each other, we'll get the real part, so this is equal to cosine of t, and this is half E iota t into minus I plus half E iota t minus E iota t into I, and this is equal to, so this is basically, this thing is minus iota cosine of t and plus minus iota square is plus sine of t, and this thing is iota cosine of t and minus plus sine of t. So again half, so this is sine of t. So U of t is cosine of t and sine of t. Good. What happens if, so if u of 0 is some AB, if u of 0 is some AB, this implies C, which is S inverse U naught, equals, so C is S inverse U naught is S inverse is half plus iota by 2 minus iota by 2, and U naught is AB. So now C1, so this implies C1 is half A plus iota B, and C2 is half A minus iota B. And what is U of t? So U of t, or U of t is half A plus iota B into x1 e iota t, e iota t into 1 minus iota plus half A minus iota B into e minus iota t into 1 plus iota, right? It's 1 plus iota and 1 minus iota, 1 minus iota and 1 plus iota. And this is equal to, if I expand this one, so this will be half A plus iota B into cosine of t plus iota sine of t, and this is multiplied by, and this is plus half A minus iota B into cosine of t minus iota sine of t, and the second one would be half A plus iota B into minus iota into cosine of t plus iota sine of t plus half A minus iota B into iota into cosine of t minus iota sine of t. So what is this equal to? This thing is equal to half, and then A cosine t, so maybe I write it over here. This whole thing, so half A cosine t, half A cosine t, so this is A cosine t, and then I have iota square, which is minus here, and plus iota square, so minus B sine t. Everything else is 0 because it's A minus A sine iota and plus A plus iota B and minus iota B. And this one is equal to minus iota, so minus into minus plus, and this is minus plus sine t, A sine t, and this one is also minus, this plus and A sine t, and then you have minus iota B minus plus B cosine t, and again here minus iota square plus B cosine t. Everything else is 0. So this implies U of t equals A cosine of t minus B sine of t, and this is B cosine of t plus A sine of t, which I can write as cosine t minus sine t, a and b. This is sine t and this is cosine of t. So this, by the way, is EAT and this is U0. So this equation is still valid. U of t is EAT U0. So if A is skew symmetric, this implies A transpose equals minus A, then EAT is an orthogonal matrix. EAT is an orthogonal matrix which has orthonormal columns. It's an orthogonal matrix because it has orthonormal columns, because EAT, when you do the transpose here, this is EA transpose T, which is equal to E minus AT, and this is the inverse. This is the inverse of EAT also. So AT equals minus A gives a conservative system, which implies no energy is lost. No energy is lost in damping or diffusion. What about EAT U0? So this simply means this is EAT U0 whole transpose. Maybe I put a square bracket here. Whole transpose. So maybe I do a square here. So whole transpose into EAT U0, which is equal to U0 into EAT or E minus AT into E plus AT, because this is transpose. Transpose, you reverse the order here, and this is transpose here, and this is U0. This is simply equal to U0 norm 2, because this is identity. And why identity? Because EA transpose T is equal to E minus AT. It's a skew symmetric matrix. Also A equals 0 minus 1 1 0. We know this implies A squared equals minus I. This is the rotation by 180 degrees. Rotation by 180 degrees. And what is EAT? So let's see what is EAT. EAT, so now EAT is simply I plus AT plus A square T square over 2 factorial plus A cube T cube over 3 factorial plus so on and so forth, which is equal to 1 here because of this I, 1 here because of this I, and this is A, so minus T here, so minus, so this is AT is T and this is minus T, so minus T on this side, minus T here because of AT, plus T here because of this AT, so this one here and this one here. Then you have A square is minus T square, so this is minus T square over 2 factorial. This is because of this one, and obviously we have minus I here, so minus T square over 2 factorial here, and then this one would be actually plus T cube over 3 factorial. This is plus T cube over 3 factorial, and so on and so forth. so on and so forth, so on and so forth, so on and so forth. And this one, by the way, is equal to cosine. This is cosine of t. This is cosine of t. It's an even function. This is minus sine of t. This is sine of t. So this is actually cosine of t, uh, which is the same matrix we found in the above example. So this is, by the way, k. This is k, 90 degrees rotation. 90 degrees rotation. This is 180 degrees rotation. So cosine of t minus sine of t, sine of t, and cosine of t. And this one is the same as, this one is same as this one. Cosine of t minus sine t, cosine of t, cosine of t minus sine t, and cosine of t. If I look at this example that we did before, A equals minus 2, 1, 1, minus 2, the symmetric matrix, my eigenvalues were, if you recall, minus 1 and lambda 2 was minus 3, and this implies a stable system because the real part of the eigenvalue is stable system because real part of lambda I is less than 0. So this is where we stop. So next time, inshallah, we are going to look at complex matrices, and once we are done with the complex matrices, we move on to the similarity transformation, and then the Jordan form. So if you have any questions, you can send me an email, or we can again discuss this on Mondays and Wednesdays. Thank you.